Swayam Prabha. Digital India. Educated India.
Hello and welcome to this lecture of the course Elements of Mechanical Vibrations. In the previous few sessions, we discussed the transfer matrix method as one of the numerical methods to investigate torsional or longitudinal or bending vibration problems. In the series, we have now another numerical method which is very common and very widely used, very popular in that sense, which is the finite element method. And although finite element method is a subject in itself and is actually being taught as a separate course, the idea behind this session is only going to give a glimpse of this method as a natural extension to the other previous numerical methods that we have seen, and see as to how the method gets applied to solve vibration problems. Okay, among the various numerical methods, the last one we are going to discuss is the finite element method, which amongst all has gained a lot of popularity and applicability. So, we will in very brief look at how this finite element method is a bit different than the other methods, the transfer matrix method based approaches that we discussed of modeling the vibratory system and analyzing it. So, this itself is a separate subject as such, and almost every engineering graduate is learning this method because of its practical application in solving complex dynamic problems. In fact, it is used for variety of engineering analysis purposes. So, we will focus only on the vibration part of it, and then look at this method as a natural extension or a natural alternative to the existing methods that we discussed on the transfer matrix approach. So, let us look at this method as a method of solving this vibration problem of a continua, and the way we did for the transfer matrix method, Holzer method as well as Michelstadt-Pröll method. Here as well, we divide this continuum into several segments small enough so that the approximation involved does not influence the net result. So, the method here as well looks at the continua as an assemblage of several small segments interconnected to each other. And in this particular discussion, we will look at this method for solving both the torsional or a longitudinal vibration problem as well as a beam lateral vibration problem. Okay. So, here to start with, let us focus on a practical system like a propeller shaft, which is expected to vibrate in the torsional or longitudinal direction, and if we discretize this into several segments, how each segment will behave or what are the governing equations involved, and how we set this up as a global vibration problem of the entire system. So, we discretize this into several elements. Each element is called as a finite element, and we assume in this particular case that each segment itself behaves like a linear spring element, quite similar to the Holzer method. So, the various steps which are typically followed is you choose the type of element that you will use for in modeling this system as an assemblage of several elements. So, each element has to be properly defined, And then we define a shape function or an interpolation function. We will discuss what this function is all about, but that's step number 2. Then we derive how each element behaves, in the sense that what are the element stiffness and mass matrices which define that individual element, and then assemble these element stiffness and element mass matrices together so as to form a global stiffness and mass matrices that will completely model the entire system. And you can then, once you obtain these system level matrices, then you can set up an eigenvalue problem, or you can set up external forcing function, so a vector describing the forces acting at different locations on the entire system, and set it up either as a dynamic force vibration problem or an eigenvalue problem. So how is that done? So we will first focus on individual elements and then gradually look at how these individual elements are assembled together. And I must emphasize here that we are going to approach this as a very simple spring element, but one can use instead of a linear spring element, you can use a nonlinear spring element and so on. But since this is a very small subset of the basic vibration theory, we are not going into the too much of details of the finite element method per se. So it, as I said, itself is a separate subject in itself, and for any further detailed discussion, you are expected to refer dedicated books on the finite element method. Okay, so element, so let us say one of such segment or discretized finite element is what is shown here, and as I said, we are going to assume each segment to be behaving like a linear spring element. So that small segment is shown here having a length equal to L. So element, a finite element has a length L. This is the length which is that of the segment, and the element has two nodes at the two ends, 1 and 2, and we define parameters such as displacements of these nodes as u1 cap and u2 cap. These are the translatory displacements at the two node points or node positions, the ends of this finite element. The caps here, which I am putting on the variables, the nodal displacement u1 and u2, are only indicating that these are defined in the nodal coordinate system, so or a local coordinate system. Similar to these displacements, we have the forces acting at the two node points or node positions. On these nodes, forces F1 x cap and F2 x cap, they act on it, and S are the forces which are acting on these nodes because of its interaction with the neighboring elements. So these are, if we assume that this element is under tension, then S is the force which acts at both of these nodes in the direction shown. Okay. All right. So as I said, elements are the parameters here which we have defined, the displacement and forces, are defined in the local coordinates, and therefore they pertain to that particular element. We are anyway now going to, once we define this the element completely, we are going to assemble these elements so that finally it forms the entire vibratory system. It's quite similar, as you would recall. We characterized each segment in a transfer matrix method and then looked at how the state variables of individual segments are interconnected, and then we formed a global vibratory system. The system will have its own global coordinates, and therefore we will show that these forces, the nodal forces F1x, F2x, we shall look at when we assemble these elements together. We will have to define these forces in the global coordinates. Now, with these nodal displacements defined or known at the node locations, make a note here that this u1 cap and u2 cap pertains to the displacements of the nodes of the element. We would like to understand if these are the nodal displacements, and if I want to know what is the the behavior or the displacement within the element, I should have a function that defines the displacements within the element, right. So, we define an interpolation function which is also called as the shape function, so that u cap, which is the displacement at any position within the element, and that position is defined as x cap, which actually is the position within the element. For a linear spring element, obviously it will suffice to have a linear interpolation function, and so we define this as a1 plus a2 x cap, right. A1 and A2 are the arbitrary constants, and we'll have to find out what these A1 and A2 are, and we know that if I use the end conditions, I can get A1 and A2 completely defined, provided I know the value of these nodal displacements at the two node locations. So, having known the node node displacement u1 cap and u2 cap to be known, we can express the boundary conditions as this u cap at x cap equal to 0 obviously will be the nodal displacement u1 cap at node 1. And similarly, u cap would be the nodal displacement u2 cap, okay, look at this, at x cap equal to L, where L is the is not the length of the total vibratory system, it is the length of the finite element, okay. With these boundary conditions specified, we can use these boundary conditions in this equation and then get the constants a1 and a2 defined, and obviously it will be in terms of the nodal displacements which are known values. So, once you put these boundary conditions, it is quite straightforward to express this u cap as a function of x cap in this form. So, here a1, by substituting this, a1 will turn out to be u1 cap, which is quite simple, you can try it out yourself, and a2 will be 1 by L u2 cap minus u1 cap. So, this now completely defines the profile or the way displacement is going to vary within the element, and this shape functions as you can see is expressed in the form of in terms of the nodal displacements, the displacements at the two node points. Once this is done, now we can relook at these nodal forces, nodal displacements accounted for. What are the nodal forces? We can see that the nodal forces are defined the way you see it here at these two locations, and these F1 cap x, F1 x cap, which is the nodal force at node 1, F2 x cap, nodal force at node number 2. These can be written as minus s and plus s, as you can expect here if the element is assumed to be under a tension, okay. So, with this done, we can now express the relationship between S and the two nodal displacement, which is quite straightforward. Now, we have assumed this to be a linear spring element, then the tension S is going to be equal to K1 times the net stretch in the element. The net stretch in the element is going to be the net deformation or stretch in the spring, which is going to be U2 cap minus U1 cap. And once this is done, you can now express or replace S in the expressions for the nodal forces, so that you can relate the nodal forces to the nodal displacements. What is the value of K1? Supposing you are now investigating this continuum as that of a circular shaft, the propeller shaft of a ship. K1, which defines now the spring character of this particular spring which you are using to represent that element, you can find that out using the geometric and material properties. So, we all know that the stiffness of a of a element which could be a circular cross section or a rectangular cross section. In the circular cross section case, it is going to be cross sectional area of that element or segment times Young's modulus divided by the length of that element, right. So, this becomes your K1. Okay. So, if we discretize this into finer elements, even if the cross sectional dimensions are in general varying, you can assume it to not vary within the small segment and then take the average cross sectional area and the material property and the length dimension to find out the numeric value of the K1. Once this K1 is known, you now have a relationship established between the set of nodal forces with the set of nodal displacements. You can show that once I substitute this S into these two equations, I will have two equations, one in F1x and one in F2x, and that in the matrix form would look like what you see here. So, what is this equation? That equation is basically relating the nodal forces to the nodal displacements in the local coordinate system or an elemental coordinate system, and that relationship is through the stiffness matrix, and that stiffness matrix is pertaining to that particular element, and therefore it is called as the element stiffness matrix. This is for that particular segment. This can be written in a short form as Fx cap as a vector of nodal forces relating the element stiffness matrix with a vector of nodal displacements. And therefore, this Ke itself will be an elemental stiffness matrix Ke cap. Okay. So, this pertains only to that element. Let us look at how do we go about extrapolating this, and how do we assemble these elements together to represent an entire system, vibratory system. So, this is the shape function that we had already discussed. In a matrix form, you can represent this to be given by this expression, shape function matrix multiplied by the nodal displacement vector. And now that if we want to see this as supposing that this propeller shaft, as you saw as a step shaft, if this propeller was discretized just into two segments or two elements, like element number 1 and 2, each having constant cross section individually, but one has a different cross sectional dimensions as compared to that of 2. If we assume this to be representing one finite element and this one as a separate second finite element, they will have to be assembled together to recreate your original entire propeller shaft. So, this is your element number 1, this is your element number 2. Each of them have their own nodal displacements and nodal forces F1x, 1 indicating that it is pertaining to the first element, and F2 2 and this F3x 2 is pertaining to the second element. And so, we can give node numbering here based on the local as well as global coordinate system. So, 1, 2 are the two node positions of element 1, whereas 2 and 3 are the node positions of the element number 2. Now, how do we join them together? We can obviously see that these forces in the global coordinates is going to be now given as F1x at this point, at this global node numbering position number 1. At position 2, it will be summation of the two nodal forces F2x1 and F2x2. So, individual nodal forces gets added here to generate F2x here, and F3x is going to be equal to F3x cap 2. So, if we do that, we already have defined the relationship between the nodal degrees of freedom, nodal displacements and nodal forces for element 1 and element 2, individually defined like this. Make a note here that in the element stiffness matrix of element 1, these K will pertain to the characteristic of this particular element, which means that the cross sectional areas could be different, the length could be different, and therefore the stiffness which defines that element will be different than the corresponding stiffness value for the second element. So therefore you have K2 defining the stiffness of the second segment or a second finite element. Once this is done and we have the relationship of f1x, f2x and f3x, we can now define the relationship between the global forces and the global displacements at each of the node positions given by this, by assembling them together. Because we are going to connect this node with this node, just like what you see here in the global system. U1 sorry, if you define this as U2 cap 1 and this one as U2 cap, which actually means that this U2 is the displacement, nodal displacement of this element, but that it belongs to the second element. That is why I have written here as U2 cap. Now because these nodes are connected to each other, they will have the same nodal displacement. So U21 cap will be same as U22 cap, right. So with that you can show that these two equations can be combined together to generate the force deflection or force deformation relationship given by a matrix which is an assembled stiffness matrix here. So once we get this the matrix relationship, we can set up an eigenvalue problem. We all know that we can set up an eigenvalue problem which we have discussed many times in the past, where in this particular equation D represents all the nodal degrees of freedom or nodal displacements U1, U2 and U3. Now U1 cap and U1 here are different in the sense that U1 cap is the nodal displacement defined in the element level, whereas U1 is in the global level in the sense that I will define this as node 1, this as node 2 and this as node 3 of the entire system. So U1 the U1 cap will essentially turn out to be U1 in this particular global system. Once we have this D defined as all the nodal displacements U1, U2, U3 and F itself representing the vector F1x, F2x, F3x, you can now represent this or write this as equal to mass times, sorry, the force which we know is actually K times the displacement, the global stiffness matrix here, which is going to be this K times the nodal displacement D vector. Once you equate this finally turns out to be in the familiar form of mx double dot plus kx equal to 0. The only thing here is that these vector D is representing the nodal displacements in the global context. And from here how to get all the eigenvalues, all the eigenvectors is all a straightforward exercise which we have done many times over for the discrete system analysis. So that part of course is a common thing from here onwards. This is how you set this discretization method through defining each individual element, finding out the element stiffness matrices. You can assemble these matrices together and you can see that in this case this particular element in this global coordinate system is going to be lying here in this particular position, whereas this entire matrix, this element is coming back here and that matrix is appearing here. Okay. So this is how we assemble it. You can see that U1 is on the first row, U2 is representing the second, and U3 is representing the third row, right. That is how they needs to be appropriately assembled together. Now we look at this method from the context of lateral vibration problem. The same propeller or any let us say wind turbine rotor can be represented like a cantilevered shaft, and that will undergo lateral vibrations. And if that is again to be modeled and analyzed, we again can assume it to be discretized into several such discrete elements, each element behaving like a beam. Now that beam is shown here, as you can notice. However, in this case it is not only the nodal displacements, but we are also going to look at the slopes at these at each of these node locations. So the nodal displacements will be in the form of the lateral motion v and the slope phi. Okay, so v1 cap, phi 1 cap becomes the slope and the displacements at node position 1 in the element coordinates, and v2 cap and phi 2 cap, these are the displacements and slopes at the second node point. So this is node number 1 and this is node number 2. So this is 1 and this is node number 2. There are corresponding shear forces and bending moments, as you are quite familiar, having discussed the transfer matrix or Mikkelstadt-Prall method. There is a slight difference here in terms of the assumed sign conventions, but that is how we define them. Like V1, Vy1, Vy2 are the shear forces at the two node points, and Mz1 and Mz2 cap, these are the nodal the bending moments at the two respective nodes. Okay, now with this, how do we establish the relationships? Now here again we look at the interpolation function, that supposing that these parameters are known at these two node locations, how do I find the value of the displacement at the intermediate point between the nodes? That basically is our shape function. However, in this case we cannot use a linear interpolation function, obviously, because the beam deflection equation involves the fourth derivative in y, and so to satisfy this equation, we cannot use a simple linear interpolation function, and this function is now a polynomial, cubic polynomial, as shown here, which will satisfy the expressions for the shear force and the bending moment. The interpolation function obviously will have to be completely defined. So A1, A2, A3, A4 are required to be established, what their values are, and the way we have done it earlier, we will basically use the boundary conditions. We know that v cap, the displacement function at x cap equal to 0 takes the value of the nodal displacement at node position 1, that is v1 cap, and similarly the slope is phi 1 cap and at x cap equal to 0. So that gives A3 and A4 values. So these unknown values of A3 and A4 are now defined in terms of the nodal parameters, the v1 and phi. And on similar lines, at x equal to L of this element, x cap equal to L, you can establish the values or expressions for the other two constants A1 and A2 using these two equations, with with A3 and A4 already known as v1 cap and phi 1 cap. Okay, so with these four conditions, you essentially express the entire interpolation function in terms of the nodal displacements and slopes. So v1 cap, v2 cap, phi 1 cap and phi 2 cap. This can be reformed into a shape function matrix, and that is given by V cap equal to n matrix n, which is a shape function matrix, times the nodal displacements. Okay, where this n, you can figure this out by rearranging this in terms of um, uh, these nodal displacements, x cap in terms of the special variable here within the element x cap. So n1, n2, n3 and n4, all these elements of the shape function matrix can be now completely expressed. So with this shape functions, the moment we get to know the values of v1 cap and phi1 cap and so on, you can get the values of the displacements at any point within the element. Okay. Now, how to get the element stiffness and mass matrix? So for the case of stiffness matrix, we again assume that the beam is a simple beam following the Euler-Bernoulli beam theory, wherein these expressions are valid. We all know that, and so referring back to the equation of the displacement v cap, we can now implement the boundary conditions here. So Vy1 cap is basically the shear force at x cap equal to 0, and for that we can use this equation. Okay, so Eizz d3 v cap by dx cap cube at x cap equal to 0, that gives us the shear force at the left node position, and by substituting it into or by using this particular interpolation function in the expression here and then taking the derivative, you can finally get an expression which is relating Vy1 cap in terms of all the four nodal displacements. On similar lines, if you use this equation, you can get this bending moment expression, and that exercise is a very straightforward algebraic exercise which is left to you to carry out and verify whether these expressions are right or not. Same thing happens at the other extreme end. The shear force and bending moments at x cap equal to L can be obtained, and once you do that, then I can establish the relationship between the nodal forces with the nodal displacements. So F cap is now going to be Vy1 cap, Mz1 cap, which pertains to the forces at the left side node, whereas these are the forces on the right side node, and they are correspondingly related to the nodal displacements V1 cap and phi1 cap and these ones. Okay, so these four relations or expressions you can reform into a matrix form, and this now again takes the familiar form of the nodal force relating to the nodal displacements through a matrix called as the element stiffness matrix. Okay, so this is how we get, by again following the basic solid mechanics, one can get the element stiffness matrix representing one finite beam element.
Okay, having seen the individual elements stiffness matrix, let us now understand how these element stiffness matrices are assembled to represent the global vibratory system, or a system which is being modeled through the discretization using finite elements. So, we take a small example here of a shaft which is having a disc at its midspan and supported in bearings. So, we treat this as a simple support, and the disc in the center is actually considered a point mass, which is represented by a 500 kg point mass in the center of the span. And as an example, we are going to discretize this continua into just two elements. You can always of course discretize this into several finite elements and then solve it through assembly process, but just to let you know how the assembly of individual finite elements into a global coordinate system is done, we restrict ourselves to only 2 elements. Okay. So, as we discussed, the continua is discretized into 2 segments. One segment is here, which is the first segment, and the second segment is here. Okay. So, just 2 segments, 2 finite elements with their individual properties. In this case, because the disk is in the center of the span, the lengths are identical, and for the case here we also consider the diameter to be the same. But having discussed this, we again go back to this finite element stiffness matrix, which is a function of the material parameters and the cross sectional dimensions. So, when the shaft is vibrating or going to bend in this vertical plane, if these represents as the coordinates x and y in the xy vertical plane, if it vibrates, then for the bending vibrations, the area moment of inertia is going to be about the axis z, right. So, IZZ represents the area moment of inertia of the beam about the z axis, and that is what will appear here. The elastic modulus will be based on the material of the shaft, and length L will be this length of the finite element. Now, once these parameters are taken numerically, one can find out the element stiffness matrix, which will represent the first element. So, I am using this as the element number 1 and this as element number 2. Now, you must understand that each finite element will be having these 2 nodes. In this particular case, we are taking this finite element as a 2 noded element, and in the nodal coordinates the degrees of freedom are V 1 cap and phi 1 cap here, and similarly the degrees of freedom at the other node going to be V 2 cap and phi 2 cap. The cap represents that the parameters pertain to the nodal local coordinate system nodal degrees of freedom. Now, the second element is going to be similar to what we have as the first element, and its own degrees of freedom in its own local coordinate system will still be V 1 cap, phi 1 cap and V 2 cap and phi 2 cap, right. The only difference will be that if the shaft diameter here is different, the flexural rigidity will be different. For the second element, we represent this stiffness matrix as you see here. In this case, the IZZ and L will pertain to the second element, which is this. Now, the most important point, having obtained individual stiffness matrices of the 2 finite elements, how do I assemble them together? Now, although these degrees of freedom are in the nodal coordinate system, in representing the original system, which I have discretized into 2 finite elements, in the global coordinate system, the node numbers which I had earlier as 1 and 2 here and then back again 1 and 2 here, I would have a node numbering to represent the system in the global context, and therefore, the node numbers will be 1, 2, 3 onwards. This being a 2 element discretization, the node numbers will start from 1 and will be the third node is going to be the last one. Now, this particular node of the first element and this particular node of the second element, they are actually coincident nodes, and it is quite obvious that this V 2 cap pertaining to the first element will be equal or same as V 1 cap pertaining to the second element, and obviously in the global coordinates, if we define the degrees of freedom, the nodal degrees of freedom as V 1 and phi 1 and here as V 2 and phi 2, and here obviously it is going to be V 3 and phi 3. So, it is quite obvious that this has to be V 2, that is the lateral motion or a displacement in the vertical plane V 2, right. And of course, it also means that phi 1 cap will be same as phi 2 cap will be same as in the first, for the first element will be same as phi 1 cap for the second element, and that should be phi 2. Okay. And through this process what we do is we assemble this matrix treating the global coordinates and the nodal degrees of freedom in the global coordinates, and therefore, this becomes element number 1 and this is of course element number 2 for us, but when you assemble this into a global stiffness matrix, this is how they will get assembled. Now, what you have in each row and column, because it is a global stiffness matrix, each column and row represents the degree of freedom or the nodal displacements at that particular node in the global node numbering. So, therefore, you can see that V 1 and phi 1 are actually mapped to V 1 cap and phi 1 cap, V 2 and phi 2 are mapped to V 2 cap and V phi cap phi 2 cap, which actually is same as V 1 cap and phi 1 cap of the next element, and that is how they appear here in the global stiffness matrix. So, let me show you that the matrix is now going to be as you notice here, wherein the first 4 rows and columns here are corresponding to the first element. Okay. So, this part corresponds to the first element and their individual elements are same as or taken directly from the elemental stiffness matrix. And what you notice here is that for V 2 phi 2 V 3 phi 3, these are the global nodal coordinates for the second finite element. Of course, there is an overlap of V 2 and phi 2 for both first and the second element. So, what you will have here is that there would be an overlap in these rows and columns which belong to the second finite element, and therefore, you will have addition of 2 elements of the element stiffness matrix, and that is how this is going to happen for the assembly process. So, what you have here is this element for the first finite element, and then this part actually belongs to the first finite element, and then of course, at this particular element position, at this particular element position, and of course, here and here there will be overlap and there will be addition of the elements such as this and this and so on. Okay. This is how the assembly is done, and now you can notice that the global stiffness matrix now would have these nodal degrees of freedom in the global node numbering, and that is how the assembled stiffness matrix will look like. Okay, having seen the global stiffness matrix and how is that formulated, let us now try and figure out how we solve this problem for getting the eigenvalues and eigenvectors. Now, in that light, it is important for us to now implement the boundary conditions for this problem. Having discretized the original continuum in 2 finite elements and having assembled them together, which now represents the entire system, let us implement the boundary conditions. Now, as we said that this represents a shaft which is supported in bearings, we assume again that the bearings offer simply support end conditions, which actually means that the nodal degree of freedom here is going to be restricted by the bearing, because if it is a simple support, the translatory motion here will be 0, and therefore, the nodal degree of freedom V 1 and V 3 both of them should be 0 for representing the simple supports. And we all know that the simple supports do offer no resistance to the slope, and therefore, you phi 1 and phi 3 will not be 0 in contrast to V 1 and V 3. So, phi 3 is not 0, neither is phi 1. Okay. So, in this case, if this is the global stiffness matrix that we have obtained, let us look at how we apply the constraint. So, the constraint as we discussed V1 and V3 are 0, and one of the simplest way of implementing these constraints in the global matrices is to remove the rows and columns corresponding to these degrees of freedom. So, in the global context, if the degrees of freedom are V1 phi 1, V2 phi 2 and V3 phi 3, we would remove the column and row corresponding to V1 and V3. So, this particular column is removed from this global stiffness matrix, so is the column corresponding to V3. So, these 4 rows and columns are removed, and after implementing that, what we are left with is the assembled stiffness matrix after applying the constraint to look like this. Okay. Now, this is your global stiffness matrix, and what will be the global mass matrix? Now, here again let me emphasize that the assumption for us was that in comparison to the mass in the center of the span, the mass of the shaft is negligible, and so we did not really consider the mass of the shaft. Now, if this is the mass of the disc, and we are again assuming that it only has a translatory inertia represented by the mass 500 kg here. So, basically the rotational inertia is neglected here, and if that is the case, then your mass matrix will only have an element at the degree of freedom corresponding to the translation here. So, about V2. Okay. And so, therefore, the mass matrix would look like this in the assembled condition, because in the assembly we all know that what we are left with is phi 1, V2 and phi 3, sorry phi 2 and phi 3. So, all of these are the remaining degrees of freedom after the application of the constraint, and therefore, a 6 by 6 matrix is now reduced to 4 by 4 global stiffness matrix, and the global mass matrix looks like this because of the assumption that there is no rotational inertia for the disc. The elements corresponding to the slopes, these are all treated 0, and of course, all other elements here are going to be 0, except the element representing the mass of the disc appears in the second diagonal element. Now, as we have been formulating this as a governing equation of motion, this basically is mx double dot plus kx, right, equal to 0 or equal to f of t. Now, is your governing equation of motion representing the system which we started dealing with. So, x here is a nodal displacement vector comprising all the relevant nodal degrees of freedom, and mass and stiffness matrices are, as you see here, compiled based on the number of discretization we do. So, if you increase the number of elements here, the size of the matrix will increase. Once we formulate this as the governing equation of motion, the subsequent solution process is exactly identical to what we have already discussed for fewer degrees of freedom in even in multi degree of freedom systems. So, the whole subsequent process is similar, that you formulate or assume the solution harmonic response and then set it up as an eigenvalue problem for finding natural frequencies and mode shapes, or if you want to find out what is the response of this particular shaft, what is the response of this shaft if the disc has an unbalance which is u omega square. If the unbalance in the shaft is u omega square, then instead of the right hand side being 0, you will have what? The excitation function here. Now, excitation function is going to correspond to the V2 degree of freedom, and therefore, u omega square, and of course, you can add sin omega t here or a cos omega t to be the excitation, time dependent excitation function for finding out the response of such a multi degree of freedom system. Now, to evaluate that response either in the free vibration case or a forced vibration case, you can again apply the modal analysis process to efficiently solve this large size matrix equations, and that is the power of modal analysis. can be handy for the solution process. So, this is how the finite element based formulation of the governing equation of motion representing a continua can be obtained, and what is important here is to understand that size of the matrix representing the original system will keep becoming bigger and bigger based on the number of elements that you have used for discretizing the original system. Whereas, in contrast, if you recall, in the transfer matrix method, overall transfer matrix remained the same size as the individual transfer matrix representing in each element. So, that is the major difference between these two approaches. However, as we have discussed, the finite element method is much more popular, and because of its adaptability to account for variety of boundary conditions and the complexities of the model. So, the summary of this lecture, we got introduced today to the finite element method, although this introduction was very basic in its nature, because we also wanted to ensure that having seen the transfer matrix method as one of the alternative, which other alternative is available for us to investigate vibration problems. The concept of element stiffness and mass matrices, how the matrices get assembled to generate global stiffness and mass matrices is what we have discussed in the lecture. And finally, you form the governing equations of motion in the matrix form, which is then in a standard way you can solve it for eigenvalues, eigenvectors, and also forced vibration response. The power of finite element method lies in its adaptability to different kind of boundary conditions, and in that sense it has gained popularity. But of course, as we must understand that the size of the matrix for a transfer matrix method is very small. So, no matter how many segments that you consider in a transfer matrix method, the size of the overall transfer matrix remains 4 cross 4 or 2 cross 2 for the Holzer method. Whereas, in finite element method, the number of rows and columns in a global stiffness and mass matrix is proportional to the number of discretization or elements that you use for representing the original continuum. And therefore, there is a computational overhead that you expect when you use a finite element method, which is not there for a simple transfer matrix method. Although of course, as I said, there are other advantages of this FE method for which it has become more popular. These are the review questions for you. And these are the answers.